Welcome, students. Good afternoon. Welcome to the 20th lecture of Refrigeration and RAC. So, we are in the unit 2. So, by today or tomorrow, we can complete the unit 2 syllabus and we can switch on to the unit 3. Okay. So, in the last class, we have discussed about the advantages, the applications of this uh, refrigeration and air conditioning. And also, we have seen some of the types of this refrigeration system and also some of the problems. Today in this class we will discuss about the analysis, how to analyze the standard vapor refrigeration systems and related problems, and also the types of compression cycles, types of vapor compression cycles based upon the change in the cycle phase. Thereby some of the calculations will change, thereby the problems are also can be done. So we will see that those things in this session. Yes. Coming to the analysis of standard vapor compression refrigeration system. Here it can be carried out by some 2 or 3 topics. The simple analysis of standard vapor compression system can be carried out by, we have to assume some parameters. Then what are those parameters here? The first parameter is steady flow. Second one is negligible kinetic and potential energy changes across the each component. And third one is no heat transfer in connecting the pipelines. So these are the 3 assumptions made for this standard vapor compression refrigeration system, so that we can do some of the analysis, right? So the simple process what we can do is the steady flow analysis and negligible amount of potential and kinetic energy and no heat transfer in connecting the pipelines. So these are the 3 assumptions made by the standard vapor compression cycle. So if you see the steady flow energy equation applied to the 4 components, what are the 4 components here? The 4 components are evaporator, condenser, heat exchanger and transferring device, expansion device. So coming to the first one, the first component of the 4 components is evaporator. The heat transfer rate at evaporator or refrigeration capacity, right? The heat transfer rate QE is given by QE is equals to M1 H1 minus H4, M1 of H1 minus H4, where MR is equal to refrigerant mass flow rate and H1 H4 are specific enthalpies in kg per kilojoules per kg. Now, which is equal to the heat transfer to the evaporator per kilogram of refrigerant. The evaporator pressure PE is the saturation pressure corresponding to the evaporator temperature. That is, PC is equals to P saturation into temperature. P saturation into temperature. Next, coming to the second component, compressor, the power input to the into the compressor WC, right? WC means the compressor pressure, work done by the compressor. WC is the work done by the compressor. WC is equals to MR, mass of refrigerant, into H2 minus H1, where H2 minus H2 and H1 are specific enthalpies at the exit and inlet of the compressor and known as specific work of compression, right? Next one, third input is condenser. The condenser rate is given by QC. Heat transfer rate at condenser QC is given by QC is equals to MR of H2 minus H3, where H2 and H3 are specific enthalpies at the inlet and exit of the condenser. Therefore, the condenser pressure PC is given by PC is equals to P saturation into TC and condensation temperature. P saturation into condensation temperature. Next one is the fourth one is a device. So for the isenthalpic expansion process, The kinetic energy changes across the expansion device is considerable. So if we take the control volume, if we take the control volume well downstream of the expansion device, then Ke will be dissipated and H2 H3 is equals to H4. Therefore, the dryness fraction can be written as the dryness fraction can be written as H4 is equals to H4 is equals to 1 minus X4 of HFE plus X4 of HGE is equals to HF plus X4 of HFG. So this is a equation for this device. Next. Next, coming to the types of vapor compression cycles. So in the last slide we have discussed about the four components where the analysis have been changing takes place, right? So the next thing to be discussed is the types of vapor compression cycle. The types of vapor compression cycle. So here the slide is not fine. Once again, please wait for few moments. Yes, so it's again back. The screen is back here. Now we'll see what are the classifications or types of vapor compression cycles. So in the previous classes we discussed about the applications of vapor compression cycles and also how it has been used and what for it is used, why it is used commercially when compared to the other vapor absorption type cycles, right? So the vapor compression cycle has four things. One is a compression type, one is a compression device, condensation device, expansion or throttling device, and evaporation. So generally for vapor compression we are having four major components: condensation, evaporation, compression, and expansion device. Second, many scientists have focused their attention to increase the coefficient of performance. So for this vapor compression cycle, what we are having four components. One is condensation, other one is evaporator, the third one is a compressor, and the fourth one is expansion device or throttling device. So in order to give some modifications, some of the scientists have designed or have changed the efficiency in order to increase the performance of the cycle. So out of them, many cycles have been came into existence. Out of them, the five major cycles for this vapor compression cycle are: what is the first cycle? The cycle with dry saturated vapor after compression. The cycle with dry saturated vapor. So compression time low, compression place low. What happens? So the air is get the water, the process is getting compressed, the liquid is getting compressed, right? So the cycle with the dry saturated vapor after compression process. Next one, cycle with wet vapor after compression. So what it is saying? The cycle with the wet vapor after compression. Next, the cycle with a superheated vapor after compression. So after compression, we are having how many? After compression, we are having cycle with dry saturated, cycle with wet vapor, cycle with superheated vapor after compression. Then before compression, what you are having? Cycle with superheated vapor before compression, cycle with undercooling. So here the top one is a subcooling, the bottom one is a undercooling or subcooling of refrigerant. So these are the major five types of cycles that have been used for increasing the performance of the cycle by making use of this vapor compression refrigeration cycle. Got it? So we will see these five things: the changes in the PV, TS, and also some of the formulas related to this one. And finally, we'll solve one or two problems so that your syllabus UT2 is totally completed. Right? Now, first one you see the theoretical vapor compression cycle with vapor after compression. So with the dry saturated vapor after compression. See, in the first thing, after compression, so you can see the diagrams, the theoretical diagram of vapor compression cycle and wet vapor after compression. The temperature and entropy, the pressure and entropy. See the temperature and enthalpy. You can see the cycle 1 to 2 compression, 2 to 3 condensation, 3 to 4 expansion, 4 to 5 evaporation. 4 to 5 is evaporation. So compression, condensation, expansion and evaporation. Next, coming to the pressure and enthalpy, pressure and PV. So here P1 is equals to P4, P2 is equals to P4, right? Sorry, P2 is equal to P3 here. P2 is equal to P3, P1 is equal to P4. Therefore, here you are having a compression, you are having a condensation, sorry. Here you are having a compression, here you are having condensation, here you are having the expansion, and here you are having a compression, right? So here we can see the entropy H3 is equals to H4. Here is equal to H3 is equal to H4. Next, a vapor compression with the wet vapor after compression is shown in the graph. Now here the enthalpy at point 2. So see at the enthalpy at point 2, the enthalpy here the enthalpy at point 2. Here the enthalpy, here is enthalpy, yes. The enthalpy at point T is found out with the help of the dryness fraction at this point. The dryness fraction at this point is obtained by equating the entropies at point 1 and 2. Therefore, upon equating by using the relation COP, coefficient of performance for this after before compression, coefficient of performance is equal to refrigerating effect divided by work done. Refrigerating effect divided by work done, that is equal to HF minus HF3 divided by H2 minus H1. Got it? Refrigerant effect divided by work done, that is equal to H1 minus HF3 divided by H2 minus H1. That is the formula for this first theoretical cycle changes in the vapor compression cycle. Now based on this we'll see one problem and we'll see the next cycle analysis. Now study the first problem what is given in the question. See the question here. Find the theoretical coefficient of performance for CO2 machine working between the temperature range of 25 degrees centigrade and minus 5 degrees centigrade. The DC, the dryness fraction of carbon dioxide gas during the suction stroke is 0.6. Then the following property CO2 is given by temperature of enthalpy is for liquid entropy. So at 25 degrees the enthalpy is 164 and the entropy is 0.59. At minus 5 degrees the enthalpy is 72, here is 0.2. Coming to the vapor side, the enthalpy is 282, the entropy point is 0.99, it is 321 and it is 1.21. So the latent heat 117.46 and 248.76. So this is a information given by this question. Now first write the given data as per the question given. So you have to think in mind about the graph of temperature versus pressure, temperature versus pressure, right? The enthalpy and entropy. So here given, see the graph in mind. See here, see the graph, the temperature T1, T4, the temperature T2, T3, the temperature T2, T3 is 298. That is 25 plus 273. That is equal to 298. And T1 is equal to T4. That is equal to 268. And X1, X1 is zero point 0.6. HF3 is equal to HF2. See here, HF3 is equals to H4. HF3 is equal to what? The H2. HF3 is equals to HF2. See here, right? Now HFT is equal to 164.777. It is in the uh, table. HF1 is equal to HF4. That is equal to 72.57. And SF2 0.597. And SF1 is equal to 0.2862. And H2 dash is equal to 282.23, and H1 dash is equal to 321.33, and S2 dash and S1 dash, HG2 and HFG1. So draw the graphs as per the figure shown. Draw the graph in the exam point of view. Whatever the question comes based upon the cycles, first draw the graph. So why I am compelling you to practice the graph or caps? So if you practice right now or if you practice today, automatically the process will be done. Now, first of all, let us find the dryness fraction at point 2. So at point 2, we have to find the dryness fraction. Therefore, that is at x2 point. Therefore, the entropy is S1 is equals to SF1 plus X1H FG1 by T1, that is equals to SF1 value plus 0.6 into HFG1 divided by 268, that is equal to 0.8431. Next, S2 is equals to SF2 plus X2HG FG2 divided by T2, that is equals to 0.978 plus X2 into 117 point something divided by 298. So take this one and take this one as 2. Next, since the entropy at the point 1 is equal to the entropy at point 2, therefore equating these values, whatever the values we got, 0.8431 is equal to 0.5978 plus 0.3941. Therefore x2 value is equals to 0.622. Therefore we know that the enthalpy at a point 1, the enthalpy at a point 1, H1 is equals to HF1 plus X1 HFG1, that is equals to 72.57 plus 6 into 248, that is equal to 221.83. Next, H2 is equals to HF2 plus X2 HG2, that is equals to 164.77 plus 0.622 into 117, that is equal to 237.83. Therefore, the theoretical COP is equals to H1 minus HF3 divided by H2 minus H1. So whatever the COP we got here, H1 minus HF3 by H2 minus H1. So we applied at this point. Now substitute the values of H1 minus HF3 divided by H2 minus H1. So after doing the calculation, we are getting the COP value is 3.57. 3.57. Next, coming to the second category, that is theoretical vapor compression cycle with a superheated vapor after compression. Right? Theoretical vapor compression cycle with superheated vapor after compression. So after compression low, whenever you are sending before pipeline device to the compressor or after pipeline, what happens to the theoretical vapor compression cycle? So initially see here, that is for vapor. So here we have done for wet vapor after compression. Here we are doing for superheated vapor after compression. Now see here the entropy and the enthalpy, the temperature entropy and the pressure enthalpy. The temperature and entropy. See the at point 1, 2, 2 to 2 dash, 3 and 4. So here 1 to 2 is compression mode and 2 to 3 is condenser mode, 3 to 4 is expansion mode, 4 to 1 is evaporator mode. Now here the temperature T1 is equal to T4. The temperature T1 is equals to T4 and temperature T1 is equal to T4 and the temperature T2 dash is equals to T3 and temperature T2 is as it is. So that is for the temperature and entropy. Next coming to the pressure and enthalpy. Coming to the pressure and enthalpy. Now here H1, H1, H2. So here because of the graph is changed, we don't know what happens in the evening. So that's why it has been changed and forwarded. Now see the enthalpy here. H1, see the enthalpy here. H1, H2 and H3 and H4. H1 is separated, H2 and H3 is equals to H4. Here also you are having compression, condensation, expansion or throttling and evaporation. Next, in this a vapor compression cycle with superheated vapor after compression, by showing in the TS and PV diagram, the cycle enthalpy at point 2 is found with the help of a degree of superheat. So if see the point 2, so the point 2 the superheated is changed downwards and normally condensed to the point 3. Therefore at this point, at this point what happens, uh, process will be changed at point 2. The degree of superheat may be found by equating the entropies of the point 1 and 2. Now the coefficient of performance for this is H1 minus HF3 divided by H2 minus H1. H2 minus, what is the refrigerating effect? H1 minus HF3 divided by H2 minus HF1. Now the vapor next. So understood. So based on this, we'll do some of the problem based upon the superheated temperature. A vapor compression refrigerator. A vapor compression refrigerator uses methyl chloride as operating substance. Now we'll do some of the examples based upon this superheated vapor compression cycle, right? Till today only shake 325 shake is present as of now. So how many students were present in the last class? మీకు ఇందాక క్లాస్ జరిగింది కదా, మురళీ సార్ చెప్పిన క్లాస్. Just message me how many people have attended in that class. Yes. Now coming to the problem. A vapor compression refrigerator uses methyl chloride. The refrigerant name is methyl chloride R40 and operates between the temperature limits of -10 degrees centigrade and 45 degrees centigrade. An entry to the compressor and refrigerant is tri-saturated and after compression now it acquires. Next, a temperature of 60 degrees. Find COP of the refrigerator and the properties of methyl chloride is shown in the table. So the saturation temperature at -10 degrees centigrade, at -10 is equals to liquid is 45.4 and at 45 degrees the liquid is 133 enthalpy. Coming to the vapor, it has been converted to 416 and it has been changed to 483 and the entropy in kg, liquid is equal to 0.813 and this one is equal to 0.0485 and the vapor is 1.6, and the enthalpy of at 45 degrees, then the entropy of vapor is 1.587. So with this data, write down the given following data. So what is the given data here? The given data, T1 is equals to T4. As per the graph, you know that T1 is equals to T4, that is equal to minus 10 degrees. Okay, na? The graph T1 is equal to T4 minus 10 degrees, and minus 10 under 273 add చేయండి, and T2 dash is equal to T3, that is equal to 45 degrees, that is 45 plus 273, and T2 is equal to 60 degrees, and HF1 is equals to 45.4, and HF3 is equal to 133 kilojoules per kg. Next, H1 is equals to 460. So table on everything is there. H1 is equal to 460, and H2 dash is equals to 483, and SF1 is equals to 0.813, HF2 is equals to 0.485, right? Next, H2 dash is equal to 483.6, and SF1 is equal to 0.813, and SCF3 is equal to 0.485, and S1 is equal to S3 is equal to 1.6, and S2 dash is equals to 1.587. So this is the following data. So based upon the points, first we'll see the at point 2. Why? Because you have a change at the point 2, phase 2, right? So this is a graph for the required figure. So in the unit 2, if you get any question in the exam point of view, so directly you can take the question at once, and first you draw the graph as per you know. Later you can do calculations, and first of all draw the graph so that you can come to know how to start the given data for the question. So for that also you can at least get or score some marks. Next, so after drawing the figure, see here the 1 to 2. At that point, the 2 has been reduced, right? 1 to 2, 2 to 2 dash, 2 dash to 3, 3 to 4, and 4 to 1. Now the temperature at T1 is equal to 263 as per given in the question, and T2 dash is equal to 318, T2 is equal to 333, and also the pressure with respect to enthalpy from here to here at 1 is H1, and H2 dash is equal to H2 dash, H2 is equals to so and so, and H3 is equals to Hg, H3 is equals to Hg. Now let us see the Cp specific heat of the constant pressure for superheated vapor. Therefore the entropy at the point 2, the entropy at the point 2 is equal to, right? Therefore S2 is equals to S2 dash plus 2.3 Cp log T2 by T1 dash. So substituting the values of S2 and S2 dash 2.3 Cp and 333 divided by 318. So upon substituting, we are getting the value of Cp specific heat. Cp is equals to 1.09. Next, and the enthalpy at the point 2, and the enthalpy at the point 2, H2 is equals to H2 dash plus Cp, H2 dash plus Cp into degree of superheat. So that is equal to H2 dash plus Cp of T2 minus T2 dash. So upon substituting this one, COP of a refrigerator we are getting H1 minus HF3 divided by H2 minus H1. That is equal to 460.7 minus 133 divided by 500 minus 460.7. That is equals to 8.34. Got it? Now the theoretical vapor compression cycle with superheated vapor before compression. In the after compression, here we are saying regarding the before compression type. Got it? But okay. Now see the graph of temperature. So 1 to 2 is a compression, 2 to 2 dash, and 2 dash to 3 is a condensation, 3 to 4 is a evaporation expansion, and 4 to 1 dash is a evaporation. That is for temperature and entropy process. Next for this one, pressure and enthalpy. Pressure and okay, next. So see the pressure and enthalpy. Here 1, 2 and 2 to 2 dash, 2 dash to 3 and 3 to 4 and 4 to 1. Here the 1 point is H1, the 1 point what you have to key is H1, the 2 point is H2, the 3 point is H3 is equals to H4. So we have categorized the enthalpy based upon the graph 1, 2, 3 and 4. Now based upon this supersaturated vapor before compression shown in the figure, the cycle evaporation starts at the point 4 and continues up to the point 11 dash with the dry saturated. Got it? So the cycle will be there for starts when the point 4 continues up to the point 1 dash. Point 4 is changed to the point 1 dash. Therefore we are getting the dry, whatever it is, dry saturated. The vapor is now superheated before entering the compressor. Before entering the compressor, it has been heated up to the point 1. The coefficient of performance may be found as a usual form of the relation COP is equals to refrigerant effect divided by vapor compression cycle by using the relation COP is equals to refrigerant effect by work done. So that is also FHY is equal to, right? Now based on this, we will see the other type of thing, that is theoretical vapor compression cycle with undercooling or subcooling. So what is the thing you are having? You are having a undercooling or subcooling. So if you see for the undercooling or subcooling, the point 1 and 2 is same as in a compressor. From 2 to 2 dash it has been changed, and that is a saturation vapor line to the condenser. In between you are having a saturation line. Later it is going from 3 dash to 3 and 3 to 4. So the process of subcooling and superheating is a process where we are keeping at the junctions of the device, right? So here also, because of the changes, in order to increase the performance, we have changed from there to here. Got it? So at that point, see the point 2, the changes has been done, and also the point 3, the changes should be done. Next. So in this case, the refrigeration effect or heat absorbed is H4 is equals to HF3. Therefore, RE is equals to H1 minus H4, that is equal to H1 minus HF3. That is equals to the coefficient of performance is equals to right? The coefficient of performance is equals to refrigerant effect divided by work done. That is equals to what? H1 minus HF3 divided by H1 minus HF2. For every variation it has been changed. Got it? So the time is up. We'll stop here. We are having some more problems. We'll discuss tomorrow. We'll stop here. And what is the attendance performance? Today the attendance is so we'll stop the class here. I have the other class. The attendance, today's attendance is only one person, that is Sheikh. So I took the attendance. Okay, have a nice day. We'll meet tomorrow's class.